Hello everybody and welcome back to part 2 of the second video for Biostats exam 2. I just ended up making the video on non-parametric tests. In class today he said he wasn't going to cover continuous. Granted it was on our homework. I'm going to trust him. I don't know if that's necessarily the right decision, but I wanted to get this video out a little bit quicker as well. Just because since we do know for sure this will be on the exam, I wanted you to have as much time with this as possible. Um, the continuous isn't that bad. It's in his week 10 lectures. I took a look at it. Um, really in the homework, it just went over those two types of not correlation, probability. Um, I don't think it's the hardest thing in the world to knock out. It's basically just talking about if two events are related or not, and how that influences probability. So I would look at that. If you have any questions about that, also just feel free to message me. I'm sure I can help explain it if you still did want to study it, just in case. But I really wanted to go over the non-parametric test because I think distinguishing these will be a big part of the exam tomorrow. I just have a feeling based on the quiz and kind of the fact that there's not a lot of math on this exam, meaning it'll be multiple choice. So with that, let's just get into it. Um, so what are parametric and non-parametric tests? So pretty much up until this point, we've been working with parametric tests. Um, what defines a parametric test? Two things really. The data is continuous, right? Because up until now we've been doing responses to doses, things in like blood pressure, or like I forget all its examples. But basically up until now it's been continuous. And the data's also been normally distributed. And this is kind of just naturally a property of continuous data if you think about it. Things are going to fall on a bell curve just because that's how things work in nature. Continuous data technically may not be normal always. It's just 90% of the time it will be. So I don't think normality is necessarily a precondition for a parametric test. I think continuous is the bigger precondition because that's actually how the math works. But I think just it occurs so often, it's like correlation doesn't equal causation. That's a statistics fact. Um, so what's non-parametric then? So this is non-continuous data. And when we say non-continuous, we really mean two things with the data types we've learned. We mean nominal, meaning very distinct categories without orders. Um, this could be like male or female sex, yes or no, agreeing to like a question on a survey, just things of that nature. And there don't always need to be two groups that are opposites. That's more of like a dummy variable. It doesn't really matter. There could be three groups. I just think of it as two. And then there's also ordinal, which if you remember are like it's similar to nominal data and the fact that they're not continuous values, but they do have some kind of order. So some of this would be like a Likert scale on 1 to 5. Right? Like those groups have order, but they're each kind of their own unique category. And you could even replace the numbers with like words. Like let's say it's a satisfaction rating. Poor could be 1. Mediocre could be 2. Good could be 3. Excellent could be 4, and outstanding could be 5. Right? So it's like we could substitute in those words. They don't need to be numbers. So essentially, since all the data we've been working with up until this point has been continuous and parametric, each one kind of has an equivalent that is non-parametric as well. And up until now, the big thing we've been working with in our parametric tests, you can see it in most of our equations. F-test have this, T-test have this, is up until now we've been looking at the mean of our data. If you go back, just take my word for it, I don't have it on this slide, but we're comparing means a lot. We're using means a lot in our equation. That makes sense, right? Average is a really good way to compare two things, their mean or their average. In non-continuous data or non-parametric data, we are actually looking at median. And this kind of makes sense, right? If we have like a Likert scale with like poor, mediocre, good, whatever I said, right? There aren't really defined things between those categories, right? We can't take an average of those, but we can take a median. We can find the number in the middle. Let's say people rank it around 3 as good. That could be our median if people on both sides generally fall into that. So that's just kind of the idea. On this test, I don't really foresee us really doing anything with medians. But this will probably be one of the key topics in our next few sets of lectures, finishing off the course. So now that we know the difference between parametric and non-parametric, let's talk about their counterparts, and kind of when to use them, because I think that will be the most important thing on this test, and it's what I wanted to stress most with this video, because really this video could just be summarized by this table if you want to memorize it. But I want to kind of work through examples in how we might see problems with these. Um, so let's just jump into it. And I want to go in chronological order of the tests we've learned so far. So the first test we learned, at least on this table, is independent one sample t-test, right? And pretty simple. This was when we were like comparing a t to like a population. It's when we would calculate our t critical values. I suppose we calculate t critical values for paired and for two sample t-test as well. But more just seeing if our set of samples, fell within like a population mean, right? That was kind of what we were doing with t-tests. They were very similar to z-tests in that regard. The equivalent to this, and this is where the table gets a bit confusing because things were double up. The equivalent to a one sample t-test is the Wilcoxon rank sum test. Now there's another rate, Wilcoxon. It's the signed rank test. It's down here. This is not the same thing. So if you remember one thing from this video, I don't know if you'd give us this on an exam, but be really careful. If it's for a one sample t-test, you want the rank sum test. So I'll link these in red. I'll probably switch up my pen color a lot throughout this video just to distinguish these. And this is doing the same thing. So before maybe we were looking at like the mean of a set of t-values to determine if they're in a population. We could do something along the lines of, let's say, since this can be ordinal data, we could compare it to, let's say, the average for this group of samples. We have a new drug, right? And we want to see, for some reason, people are rating our drug. Instead of a mean, we'd have a median. So let's say, again, good is our threshold. Let's say enough people are ranking it within the good category. That would be like our statistical significance, right? Instead of having that ordinal mean, how many people like it on like a numerical scale 1 to 10, we now have it, people rank it in the good category, a statistically significant amount of time. And then I also want to draw these over on the table. So this can be classified as categorical and single data for this first one, right? Because t-tables at the end of the day, they're just categories, right? Whether that be comparing different drugs. Drugs are a category. In this case, we have a single category, so it's a t-test. As well as, since this is non-parametric test, it technically fall into this one over here, but I don't like this side of the table because it literally just says logistic regression, logistic regression. We haven't learned that, so I'm linking these up to the table with tests we're familiar with. But it's the same thing, right? Just remember that for the Wilcoxon sum, it's actually dichotomous data or non-parametric or non-continuous data. They really all mean the same thing in this case. So that's our single t-test. For a two sample t-test then, what we have is we have the Mann-Whitney U test. If you remember our two sample t-test, we really only got one problem on this in class. So this is, I'm just going to highlight the S in samples here to remind you it's two samples. It was a problem we were given in class, and it was like two sets of screws, and we had to determine if these screws were in the similar population. I think we did a confidence interval with them. So this isn't comparing it to a population mean. This is comparing two samples to each other to see if they are statistically the same. That's what the Mann-Whitney test would do. So let's say for the sake of our drugs, we messed up the data with our drugs, right? We have our data got split, and we're a big company. We have multiple drugs. So we have 30 samples of our Likert scale we've been talking about, right? Our poor, mediocre, good. And we have them grouped. We know they're grouped. But we have one sample, let's say the median is mostly mediocre for the one sample. It doesn't really matter the specific numbers. And the other one, they're mostly good, like we've been talking about. Depending on how we rank them statistically, we can determine if maybe these are the samples missing that we got switched up, right? We can see if these two samples are from the same group, or if the mediocre samples, we're just talking about another drug, because we're a big company and we don't always make good drugs. These might have been a mediocre drug. So that's how we do that in an ordinal way. versus something like screw size, like obviously you can just look at a mean. That's much easier to grasp conceptually. Um, but this is essentially comparing two samples to see if their ordinal rankings are the same. So if we draw the line all the way over here, this would probably still be in t-test category. Again, this isn't like a perfect chart. I don't like it as much, but it's just easier than drawing my own. So I'll just do my best to improvise. So next up, what we have is we can finally move on to the paired t-test. The paired t-test is probably one of the more useful tests we've learned in this class. If you remember the example we got, this is essentially like your cause and effect drug, right? This is when we measure something like blood pressure before a drug was administered and then after a drug was administered to see if the effect of the drug was statistically significant. Because it was technically one sample, but we had two groups based on the condition like before and after the drug. This is the Wilcoxon matched pairs / signed rank test. This would be, let's move away from our satisfaction Likert scale now and into, we'll use the blood pressure example. Let's say just blood pressure range-wise, we use a Likert scale again, right? More ordinal data. Let's say we have three categories. Blood pressure is poorly controlled, right? Let's say these patients, even after taking our drug, are hypertensive. Their blood pressure is still above 140, but we don't rank it that way on our survey. We just say bad or poorly controlled. Then we have good. Let's just say our patients are in range from like 110 to 130 in this range. This could be our well-controlled. And then let's say we have like blood pressures systolic less than 100. This could be our over-controlled section, right? So ordinal data, these categories that have ranked. And then we could see before and after giving this drug, if we have most of our people fall into well-controlled, into good, or if we have it over-controlled, which would also be statistical significance if we have an antihypertensive, if we're always lowering blood pressure medication. But in this case, we're seeing what groups they fall into, as opposed to just the actual net change. So that over here would be, I think it'd just be t-test again. Don't take this part of the chart as seriously. I'm trying to like relate it, but I haven't looked at this ahead of time to be entirely honest. And I'm sure there's exceptions to my rules. Just mainly try and keep up with the analogies, I would say. Being able to compare and switch these two modes in your mind, because I think that's going to be a really big part of Thursday's exam. Next test I want to talk about is we'll move away from t-test, just like we did in this course, into one-way ANOVAs. So right, remember, one-way ANOVAs are super similar to two-sample t-test. The main difference is that they have more than two samples, right? Because if you remember from our last video, if we want more than two samples with a t-test, we have to do the Bonferroni correction. It's a pain. Nobody ever uses that test because it's super hard to get significance. So we use ANOVAs instead, or f-test. Same thing, really. And this, we'll start with one sample, or one-way f-test. Essentially, like, we have three samples. We just want to compare if they're statistically significant to each other. Our equivalent to this, to a one-way analysis, is this Kruskal-Wallis analysis. Kruskal-Wallis goes with one-way f-test. And essentially what this would do is, an ANOVA could, like, let's say we had three samples. We wanted to see, we can use the blood pressure example again, how much each of these samples lowered blood pressure on average. This is a similar thing, but we have three samples, and it could be, let's say we use our categories, right? Poor blood pressure control, good, and then over control. We could see if, let's say, two of these drugs just had poor control, and then one of these drugs was over controlled. Our Kruskal-Wallis test would be able to show us that between these categories. Again, it's ordinal data. So it would only be those categories, but we would be able to see that statistical significance by comparing the groups this way. And this would just be something you use for 3 or more sample groups, would be where you use it. So this could also go in ANOVA. Next up is our two-factor ANOVA, or two-way ANOVA. It doesn't really matter what you call it. If you remember, this was kind of like the example Dr. Kim did in class. This was where you are essentially comparing two independent variables to a dependent variable, right? So I think in her example, it was like drug formulation and then maybe order of doses administered. I don't remember exactly, but it was something along those lines. So for this, we could do a very similar thing. And it's interesting because order of dose administered is actually kind of ordinal data within itself, right? Because you're either first or you're last, at least if you're doing two samples. Uh, so that's where the lines get a little bit blurry. But instead of doing, I guess in a lot of ways, actually, that example is very similar to I'll spoil it, the Friedman test. Maybe I think of a different example for this. We'll use blood pressure again, right? So we'll do the two drugs, right, which are inherently categorical. Yeah, actually, that's crazy. I'd never thought about that until now. That's basically just categorical data. So two-way ANOVA actually should come very naturally, just in the sense that it's already kind of broken into categories its effect. Maybe instead of outputting like a mean though, we could output it into our ordinal ranking system, right, of how well it controls blood pressure, if it's in that poor, good, or over-controlled area. Um, Similar thing, right? You're just comparing two independent variables and then it's outputting a dependent variable. But what you're really concerned about with two-way ANOVA, and this was talked about more in the last video, was the relationship between the independent variables and not the relationship between the independent and dependent variable. So yeah, we could just use our two drugs and then I guess still order, and we could just see put it into those categories again. I think that'd be the best way to look at something like this. So that would be ANOVA still. Um, if you remember, ANCOVA was more of a regression model in itself, even though it did have two independent variables and one dependent variable. Just wanted to bring it back to that just to make sure that was kind of clear why we didn't group that with ANCOVA. Um, and then finally, the one I want to talk about, the last really one-to-one, at least that he talked about today in class, or that he had in his slides today in class, was Pearson correlation and its equivalent. So if you remember, Pearson correlation is essentially, right, you want to see how linked the independent variable is to the dependent variable or to the response. If we give a drug, right, how much does it lower our blood pressure by? And does the drug do it consistently? Is mainly what we're looking at. It's not just the lowering effect, but how consistent is it in lowering? So that's Pearson. There's actually two different kinds of tests we can do for basic Pearson correlation. We could do Spearman, which is a valid option, or we can do Kendall coefficient, which is another valuable option. So when do we choose which? So one way you can immediately differentiate these two is if it is nominal data, you pick Spearman. Spearman data can be used for nominal or ordinal data. So let's say we have a data set, right? We can use our blood pressure example some more. Let's say this drug, if we're in the over category, over controlled, we have hypotension, right? We have all these adverse effects. Maybe nausea, vomiting, just all these things. Dizziness would be a big one for hypotension. We could, instead of like ranking the frequency of those, essentially break that into categories with Spearman correlation. Do they have side effects from hypotension? Yes or no? Those could be our on and off categories for nominal. And with that, we could rank it as a Spearman. Where we'd use a Kendall correlation, however, I have no idea where I'm putting this. Oh, right there, correlation analysis, perfect, look at that. For Kendall, Kendall only has ordinal data. But if you remember, Spearman can also have ordinal data, as well as being nominal, just depending on the study. The key to Kendall is when you prefer Kendall over Spearman, is when the sample size is really low. Kendall is more effective for low sample sizes, so I'll even write that. Low sample size. Kendall. So this you could even think of something like, this could be our, again, our not well-controlled hypertensive, our well-controlled normal range, or over-controlled or hypotensive patients. And let's say this is like a phase 1 clinical study, right? We have 10 people, we're just mapping adverse effects right now at like a non-therapeutic dose. But let's say even at a non-therapeutic dose, it still makes them really sick for some reason. Or maybe it doesn't. Maybe it just doesn't work that well. And we have hypertension. This is when we use a Kendall correlation. Because if you remember, phase 1 studies only have like 10 patients. Or patients isn't even the right word because these are just healthy members of the population. 10 people tested with these drugs. and the sample size is so small, that's going to skew anything, right? So for that, we would use a Kendall. And we could use our categories of like hypotensive, hypertensive, and normotensive, to kind of rank them. So I hope that helps kind of give an idea of when we link or how we link these samples to their counterpart. Um, Obviously, with things like Pearson, it's a little more complicated just because there's more than one test, or the two types of Wilcoxons, which is kind of just memorization at a certain rate. Um, yeah, and then I'll just really quickly go over this last table. We kind of talked about it in the previous video, but I'll like link it with arrows just to show you. So one sample t-test is essentially the same as a z-test, right? If you remember from our first video, the only real difference is you can use a z-test if it's over 30 samples. That's usually big enough where the difference in data doesn't matter. And then this all could be linked to a... Oh, that's awesome. It looks like Wilcoxon isn't in this table. Well, we will write it down. So Wilcoxon... And remember, this is the ranked sum. Rank sum. So we can link that all the way down here. Perfect. Next up, we will talk about our two sample t-test. Again, similar, but this is a link with our Mann-Whitney, which is also not in this table. Look at that. So Mann-Whitney U-test. And then I'll already preemptively write the next Wilcoxon. The Wilcoxon, this one was sign rank. Sign rank. And if this matching part doesn't really help you, feel free to click off. I'm pretty much just going to finish on this. Just showing again how they rank. I might talk about some of their variables, but I talked about most of that in the previous video. So now this is just kind of another way to visualize it, right? So if it's a t-test, right, we have three types. We have Wilcoxon rank sum for one sample, Mann-Whitney U-test for two sample, and Wilcoxon sign rank for paired t-test. One-way ANOVA, if you remember, is our Kruskal-Wallis, which is also not in. Oh my goodness, I thought this table had a lot more. Kruskal-Wallis. So that's all the way down here. Remember, we use this instead of a t-test because there's usually like 3 or more sample groups. Two-way ANOVA is our Friedman, which upon inspection is also not in there, so we just get to write more. Great. And I hope this color system helps as well. I'm trying to keep it consistent throughout. I feel like visual things like that help me remember. And honestly, with some of these tests, it might be helpful to just make a flashcard deck of like 6 or so flashcards, just linking the two back and forth, get that memorization down. Because since we're learning so many new tests at once, it really is just a memorization game. And then for Pearson coefficient, this one is actually on here, which is nice. Or correlation in this case. We have Spearman. And then we also have another type of correlation all the way to Kendall. Oh, and regression is right here. Perfect. Look at that. And then one more I guess I can talk about is kind of the variables. So the only test, there's 2 of them, that will have multiple independent and dependent variables. We talked about this. This is your MANOVA, your multivariate ANOVA, as well as your canonical correlation. So these two are kind of linked in a way. They're not opposites like parametric, non-parametric, like we've been talking about this entire video, but they are important just to kind of be aware of. All your t-tests are pretty similar. Something that will have multiple independent variables, but one dependent, or 2 things, or you have your multiple linear regression, and you also have your two-way ANOVA. Technically, two-way ANOVA maxes out at 2 here, and multiple linear regression can have many. But let's just assume for the sake of this, they're both 2 for this experiment. So these 2 are kind of linked. It's just what are they talking about that's different. So in a two-way ANOVA, you're looking at the relationship of the independent variables. In multiple linear regression, you're looking at the relationship of the independent variables to the dependent variable. And ANCOVA is also very similar to multiple linear regression. I would argue even more so than really two-way ANOVA is actually. So I'll erase this big line. ANCOVA is similar in the sense that you are looking at many independent variables. I mean, these two are similar, right? Oops, it's the wrong pen color. Sorry. A two-way ANOVA is doing the same thing. It's just ANCOVA can have more than two sets, where two-way ANOVA can only have two sets. So essentially those are all similar. I would group those. And then like t-test, z-test are like the same thing. Yeah, at this point I'm just going on and on. So with that, thank you so much for watching and good luck on Thursday.